Dear colleagues, welcome back. Let's continue our session. We still have full presentations, so I guess we will finish this session at around 1 o'clock. But in the afternoon, the preliminary session starts at 1:30, so we will have only half an hour for our lunch. So let's start now. Next presentation comes from Ernestine Atangana. The topic is assessment of groundwater geochemistry and contaminant sources at Limburg Cemetery, South Africa.
This one is up, this one is down. Yeah. Up, down. Okay. Good afternoon, everyone. Okay, my name is Ernestine Atangana. Today I'll be presenting to you my topic of assessment of groundwater geochemistry at the Limburg Cemetery in Bridge, South Africa. So I would like to take you all about what is important about groundwater and also the threat. So you all know about groundwater, which is vital for drinking, agricultural, industrial, and the ecosystem. So the threatening of groundwater, it has been caused by over-abstraction, climate change, and human-induced contaminants. So the key pollution for groundwater comes as a result of the mining industry, the livestock farming, and also from the cemetery. So these challenges has been highlighted due to the Sustainable Development Goal 6, which require access to clean water for all. So I'll brief you guys through cemetery as a pollution sources. So cemetery-related pollution, such as toxic substances, which including the emerging embedded fluids, and also CO2 that comes from the cavern. So these pollutions, as a result of what? They comes from due to the permeable soils and areas with low shallow groundwater. So this issue has also been highlighted due to the SDG Goal 3, which require good health and well-being for all of us, and also the life on land, which is due to what the impact of the human and the ecosystem. So I'll take you guys to the South African context of South Africa. So in South Africa, we realize that the problem related to groundwater has become a major issue due to what? The rapid urbanization, as well as the intensive agriculture that takes place in our country. So all these are signs of what? All these cause pollution that comes from salinity, nutrients, heavy metals, ions, and as well as sedimentation in our area. So in order to fulfill this gap that we have realized that is caused by all these pollution sources, so this study is going to focus on the groundwater cemetery that is impacted in the semi-arid area here in South Africa. So therefore, our study area aims to what? Assessment of a comprehensive pollution groundwater assessment by applying a combination of indices by using water quality index, comprehensive pollution index, geoaccumulator index, and the hydrogeological processes that takes place in the environment, as well as to use the multivariate tool to make use of our study area, which is based in the Limburg Cemetery here in South Africa. So in order to fill this gap, we are going to assess the groundwater quality using those tools have been mentioned, and also to provide better decision-making for those who are in charge of who are using the cemetery as a point of solution. So where is our study area located? This is our study area. Our study area is located in the Northwest Province. You can see there. So the climate in that area is mostly experiencing hot summer and dry winter, which normally picks up rainfall, most especially in December. So the topography in that area is mostly flat, and there's mountains which occur in that, normally in the east. So the geological formation are mostly due to the Bruce-Mills igneous complex, which is rich in minerals like the platinum gold, the platinum gold mining electrode. So the geology in that area is mostly made up of fractured rocks and intergranular aquifer. So to recharge groundwater in that area, they normally use the normal rainfall and also due to the surface and groundwater interaction. So in this study that was done with one of my students, so where I assisted her, so what we did, we did sampling for 6 months. So groundwater was sampling for 6 months for a period of September 2023 to a period of January 2024. So we sampled boreholes, as I said, for a period of 6 months using the Porch method with respect to that ISO label method. So we sample for physiochemical parameters, bacterial parameters. Yeah, so those physiochemical and bacterial parameters, we have a sample on site, and they were sampled in the 500 ml plastic bottle for the chemical parameters, and the bacterial parameters were sampled in 250 sterilized bottles. So physiochemical parameters such as TDS, pH, and EC, they were sampled on site using the water quality meter, and they were transported to the nearby lab for within 24 hours. So there in the laboratory that we transported the sample, so we did measure for the physiochemical parameter as I mentioned earlier. So we measure the physiochemical parameters such as the total hardness, total alkalinity, TDS. So this was measured using the method which is specified above, the titration method, and they measure ions such as the cat ions, which are sodium, potassium, calcium, and magnesium, were analyzed using ion selective electrode. Then the anions such as the chloride, sulfate, and bicarbonate, they were analyzed using the gravimetry method. So we also analyzed for nutrients such as ammonia and nitrate. This was analyzed using spectrophotometry method, and also trace metal. About 16 trace metal was measured, such as the manganese, aluminum, iron. So they were measured using inductive coupling plasma spectroscopy. So microbial samples were also measured, such as total coliform, E. coli, and hetero count plates were also measured using magnification and culture. So the data that we got from the laboratory, we analyzed them using bivariant and multivariant statistical analysis. So for our water quality data that we got from the laboratory, so there are various guidelines in South Africa that we normally use to assess our water quality. So we use the South African national guidelines, which is SANS, and the World Health Organization guidelines, as well as the ones for the South African guidelines for domestic use, agricultural, irrigation, and also livestock farming. So for our analysis, as I told you, we measured our parameter with regard to the guidelines. Though we also use statistical tool and hydrochemical process to assess our water quality data. So for the hydrochemical processes that govern the factors of water chemistry and its possible source that were identified, that were analyzed using multivariant statistics. So for the hydrochemical process, we use pie diagram and Gibbs plot and ionic ratio to analyze it. Then for the statistical method, as I mentioned earlier, we use correlation analysis and cluster analysis to identify the source of pollution. So for our water quality, we also analyze using water quality indices. What are these water quality indices? Water quality indices, these are tools that helps to analyze water quality based on what? They analyze water quality based on the partial and the temporal variation with regard to the various guidelines that are being used. So we use various water quality indices. For example, the water quality index, we help to identify the overall general pollution on the area. So the water quality index, which stands for WQI, which is equal to the sum of the weighted value times the sum of the quality rated value, which gives you that formula. So which W is the weighted assigned value, then N is the number of pollution that is in that parameter that is in the area. So we also use another quality guidelines called the comprehensive pollution index. So this comprehensive pollution index identified the targeted polluted parameter that is that area with regard to the water quality guideline. So we use this formula: CPI is equal to the sum of PI, where the P is the individual parameter, polluted parameter, and N is the number of monitoring parameter that we use. So remember, in total, as I mentioned earlier, we sampled 27 water quality parameter. So our N now stands for that total number of parameter we use, which is 27. So the other water quality indices that we also use the heavy metal pollution index, which identify the targeted heavy metals in that area with regard to the water quality guidance. So we use this equation, which shows HPI is equal to the sum of WI cure I over WI, where where WI is the weighted value times the quality ratio guidelines value divided by the weighted value of that area. So we also use this Joe accumulation index to determine the water qualities in the area. So the Joe accumulation determines the water quality with regard to the anthropogenetic sources to verify where they are coming from. So we use this formula, and Joe accumulation index is equals to the CM of the sample divided by 1.5 times the background value. So with regard to our findings that we got, if you can see those dots I highlighted in red. So we realized from our result that we got physiochemical parameters such as the pH, TDS, they were above the guideline limit for domestic drinking and also irrigation use, as well as nutrients. If you can see there, fluoride and chloride was also above the guidelines throughout the sample period for 5 months. That took place from September 2023 to January 2024. And also we realized also the anions such as the sulfate, the anions such as the calcium, the cations such as the calcium and the magnesium were also above the guideline limits that we use for drinking, irrigation, and domestic use throughout the sampling period. While for the bacteria, we observed that the bacteria such as total coliform and heterocount were above the guideline limit for a period for just November during the sampling. So those you see that were highlighted in red are those that were above the guideline limit that I mentioned earlier. So for the hydrochemical processes that we realized, we checked with regard to our water quality guidelines. So we use pipette to analyze this. So we observe there are two types. We observe there are two ions that are located at the bottom. So if you check there at the pipette diagram, you can see the magnesium and the magnesium and the calcium, they are dominant parameter, which are due to what? The hardening of the metal. Then there's another plot that is plotted above. If you check, there's a plot that is plotted above there. It shows the dominant species for what? It shows the chloride and the sulfide, which are plotted above the pipette diagram, which also causes the hardening of the metal. So with regard to our Gibbs plot that we also plotted, we realized there's a relationship between our ions such as magnesium and sodium, as well as calcium and sodium. So that relationship between the ionic ratio between the calcium and magnesium, which is a dominant anions between all of the two of them, shows that calcite is the main source of where the pollution is coming from. And also, we also realized that the level of chloride in our Gibbs plot exceeded the level of calcium, sodium, as well as magnesium, which are all of them indicating the anthropogenic sources. So you can see all our pollution sources that are attacking our hydrochemical processes. They are mostly from the anions. So for our statistical analysis that we use the cluster and and the Pearman correlation analysis. So if you can see, the Pearman correlation analysis shows that there's a strong correlation between our anions, our physicochemical parameters such as EC, which is correlated with those anions like fluoride, nitrite, calcium, and magnesium, with those values arrow value. We show that they are statistically significant, while there's a strong negative correlation between our fluoride and also our magnesium, manganese, and calcium, which shows those strong positive correlation. Then our cluster analysis shows that there is a high similarity between the cluster diagram of which mesh as cluster 4 and cluster 14. If you check on the graph, why there's a similar and why after this similarity now decreased to 96%, which where the cluster they were trying to match. Then the overall cluster analysis shows that there was a single cluster which is located there at 91.2%, which shows that there's a relationship between the groundwater parameters. So from our pollution sources that we realized using the different indices, so what we realized that our water quality index that we use indicate that the water quality is good, is excellent, and as it's excellent, it gives you the water quality rating of 2.60, and this shows that the water quality can be good for drinking and other purposes. And the only pollution source that can be dominating there is the nitrite and also the microbial contaminants. While the comprehensive pollution index that we also use, it shows slightly pollution with regard to the guideline range. It shows slightly pollution, and the pollution can be originated from the organic and inorganic ions. So for the heavy metal pollution index, which gives you a range of 60.31, it shows that it's a poor water quality. You remember from the table that we have, the heavy metal were not really showing any rule in the pollution. So here it does not really, it does not really impact in the result, the heavy metals. So for the geoaccumulation index, it also revealed that the pollution are they are not really acting too much they are not really acting too much and strengthening the work. So, but we realize that the physiochemical parameters such as TDS and the anions such as the nitrate and the metals such as the cadmium. So these metals, they come accordingly as some of the pollution that were highlighted due to the anthropogenic sources. So we realize from the different pollution indices that we use, the CPI and the geoaccumulation index, they move from slightly polluted to moderate pollution, while the other ones shows better result compared to the HPI and the water quality index. So what is our conclusion? So we are concluding from this study that was carried out in the Lambert Chemistry that was carried out during a period of 5 months, that some of the pollutions as a result of due to the presence of the physiochemical parameter such as TDS, total hardness, chloride, nitrate, while ions such as calcium and magnesium are the ones that are caused from the human decomposition. So heavy metals, as I said, was not really playing a significant role because most of the parameters observed during the heavy metals were less than 0.01, so they were really insignificant in the study. Then when it comes to our different pollution indices that we use, the comprehensive pollution index, heavy metal pollution index, and water quality index. So the comprehensive pollution index, so the comprehensive pollution index, it categorizes the water qualities to be to be slightly polluted. So it is. So we realize that it is the best indices that was used to characterize the water quality compared to the other water quality indices that were used. And also based on our statistical analysis that we use, such as the multivariate and the cluster analysis, it shows that there is a relationship between the groundwater contaminants and also the barriers from the symmetry contaminant that we got. So we are giving recommendations to our users out there that are busy busy with such study, that we must keep on continuing monitoring in such area, and also we must improve monitoring in this type of area, and also we have to update our regulation due to this type of area, and also we must keep on doing many continuous serious geochemical assessment in order to see what will happen in the nearby future. We are also encouraging green technology, green technology that it should be used in order to source our pollution, as well as also to improve awareness of groundwater programs that are being taken on in the area. So these are my references. Thank you.
Thank you. So our next presenter will be Vindaya Kandasamy. The topic will be development and real-time monitoring of a reactor for integrated carbon dioxide capture and algal biomass production using functionalized hydrogel beads. Welcome. Kandasamy, are you here? It seems he or she is not here. So maybe we can skip this presentation. Let's go to the next one. Next one will come from Emmanuel Idoko Ono. The presentation will be a comparative evaluation of orifice and slotted plate performance. Welcome.
Thank you, Chair. Good morning, colleagues. My presentation this morning is on a comparative evaluation of orifice and slotted plate performance. A deployment of an inexpensive flow metering device in municipal water management is key to keeping CAPEX and OPEX at reasonable level. The differential pressure meter plays an important role in this regard. Orifice plates and slotted plates, two potentially important components of this architecture, were evaluated on a test rig built in compliance with ISO standard 5167 with beta ratios of 0.5, 0.45, 0.43, 0.40. The resulting coefficient of discharge for the two plates indicate a higher value for the slotted plates when compared to the orifice plates, suggesting a lower energy degradation and better flow recovery for the slotted plate. In addition, the percentage CD fluctuation across beta ratio values was comparatively minimal for the slotted plate. The background to this study is flow metering, as I mentioned earlier. Flow measurement in industries is crucial for several reasons: process control, quality control, environmental monitoring, and energy management. But there exist challenges in this process, one of which is ensuring accuracy, and the second is dealing with varying fluid properties, maintaining calibration. Amongst the metering devices that we use for flow measurements in industries, the most cost-effective and simple device that we use are the differential pressure meters, and they include a range of differential meters: venturi meter, pitot plates, orifice plates, slotted plates, and a few others. They are quite simple to install, maintain, and regulate, but amongst them still is the basic and simple one to deploy is the orifice plate. It's been in use for a very long time, and a large number of it is deployed in measuring industries, water supplies, custody transfers for liquid and gases across the globe. It's very simple and reliable, but a high energy degradation and fluctuation in calibration remains a challenge for even the orifice plate. A slotted plate is therefore an adaptation, to basically address some of the issues that have been observed with slotted plates. As you can see on the sketch, the charts, we have the way they are installed, and the governing theories that guides their operation. Normally they are installed on flanges, and we have differential pressure meter tapping upstreams and differential pressure meter tapping downstreams. And the distances of those from the flanges where the plates is installed is governed by the ISO standard. The theory governing these, of course, we have the nomenclatures, is the Bernoulli expression, principally the Bernoulli expression. We have the head pressure component at the upstreams and the kinetic energy component at the downstreams. That equals the head pressure component at the downstream and the kinetic component at downstream. If the level is the same, the potential component are eliminated. And then the flow rate is given by that, which is, of course, the cross-sectional area of downstream area, particularly around the vena contracta. You don't have the sketch for that here, but the flow rate is a function of the product of the area at the vena contracta and times the coefficient of discharge divided by 1 minus the beta ratio raised to the power 4 square root times those components, the differential pressure P1 minus P2 times 2 divided by density. The beta ratio expression is given there, which is a square root of the number of plates, the number of slots divided by the cross-sectional area of the vena contracta divided by the area at upstreams. And of course, the mass flow rate expression is stated there. The last expression is the second order radial momentum of axial momentum. Those are the theories we built the test protocol around. The test protocols and experimentation include the test bench was set up in accordance with ISO standard number given there. We have 4 sets of orifice plates with beta ratio 0.5, 0.46, 0.43, and 0.4, and the equivalent sets of slotted plates with beta ratio 0.5, 0.46, 0.43, and 0.40. And the flow bench adaptation are shown there, the orifice plates and the slotted plates. And of course, we have the YouTube manometric tapping depicting how we tap the differential pressure. Typically, we feed that into a transducer, Fourier transform, and then we interpolate the signals to give us flow rate expression. The results are given above. The plot of discharge coefficient versus beta ratio shows clearly that the slotted plates has a much better, performance in terms of normally the beta ratio ranges between 0 to 1, and the higher the number, the better the energy recovery and the flow recovery. So we see clearly that for the slotted plates, the performance is much better than the slotted orifice plate. And then, of course, we have a trend of the coefficient of discharge against the momentum flow. And what we can observe for both the slotted plates and orifice plate across all the beta ratio is that there is more, the fluctuation for the slotted plates is for the 4 different runs that we had in the course of testing the flow on the flow bench, that the slotted plates fluctuation is minimal compared to the fluctuation for the coefficient of discharge, for the orifice plate. This is important when you're trying to do consistent calibration of flow. The lower the fluctuation percentage, the better the flow accuracy calibration, particularly when you are having different types of flow condition, vortex shading, eddy formation, flow separations, cavitations, downstreams, and you have other equipments that are in place that could be impacted when the flow condition becomes adversarial for the equipments that are on stream. So we see here that the coefficient of discharge for beta ratios 0.4, 0.43, 0.46, and 0.5 for the slotted plates basically are much better than the orifice plate momentum trend. From all indicators, the slotted plate has a much better performance than the orifice plate data showed. It has better head loss for a given beta ratio and flow rate, faster pressure recovery downstream, often needing no flow straightener, which is another device that becomes important when you're using orifice plate. We observe that as the performance of the slotted plates becomes, improved, it's much better improvement than the orifice plate. There are some devices that you no longer need on the flow bench. We don't need straighteners anymore. We don't need longer lengths of pipelines to try to condition the flow to create room for flow recovery. We don't need that. We also discovered that it has smaller eddies, vortex shedding downstreams, less dependence on swirls, and then, of course, less variation of CD for slotted plates than for orifice plate, indicating that the slotted plate maintains calibration over a wider range of inflow condition than the orifice plate. So our conclusion was that for better flow operability and repeatability, a slotted orifice plate is preferred over traditional single-hole orifice plate. The second is that to maintain accurate and consistent calibration, slotted plate is better than an orifice plate. Where the flow contains substantial debris media, to avoid entrainment, a traditional orifice plate can be deployed. For large diameter of flow deployment requiring any form of pigging for pipeline integrity test or to maintain, neither meter is suitable. That's obvious. So thank you. That's my reference. Thank you very much.
So now let's come to the last presentation this morning. The last presentation comes from Egerton Hingeston. The presentation title is Probabilistic Stability Analysis along Selected Slopes in the Chase Valley of Peri-Urban Pittsburgh, Eastern South Africa. Welcome.
Thank you, Chair. Good afternoon, everybody. I'm here to present on the topic probabilistic stability analysis along selected slopes in the Chase Valley of Peri-Urban Pietermaritzburg, Eastern South Africa, which was a project my colleague and I supervised a student on. So landslides are significant geohazards which are liable for socioeconomic losses worldwide. As you can see from the figures on the right, the two figures, these are landslides that occurred in Durban during the flood period. So thick unconsolidated sediments on steep slopes are common sites for spring seepage owing to the disturbance of groundwater zones and the permeable nature of the debris. So when you have formal urban development and informal housing settlements which are built on these areas, they are areas of potential risk. So the Chase Valley area of Pietermaritzburg is characterized by thick talus deposits, which is highly susceptible to slope instability. And the geological, geotechnical, and hydrogeological properties of the talus materials are poorly understood, including how it impacts on slope instability. So we investigated the stability of this Chase Valley area with a focus on a probabilistic approach to account for the uncertainty in geotechnical parameters. So this represents a study area which is located 7.5 kilometers from Pietermaritzburg, and Pietermaritzburg is about 75 kilometers from Durban. That is figure 1 showing where the study area is located, and figure 2 shows the digital elevation model of the area with the drainage map superimposed on it. In terms of geological setting, the local geology of the area is characterized by shales of the Pietermaritzburg Formation, and on top of that shales we have this talus material, which is an unconsolidated deposit. So this talus deposit forms an unconfined groundwater condition, and where you have strong hydraulic conductivity, contrast between the talus deposits and the underlying bedrock, which is shale. And where you have prolonged duration rainfall, the water that has been infiltrating through the more permeable talus deposits will be unable to percolate at the same rate into the bedrock. So this creates a localized aquifer condition in the talus deposits, increasing the water table and thus increasing the pore water pressure, causing the slope to become unstable. So in terms of the methodology we adopted in this study, we undertook a desk study which involved going through geotechnical reports, bore logs, inspection pits, results from laboratory reports, and this figure 4 shows the position of all the borehole pits and inspection pits. And then we did a field walk to instability sites, to sites of slope stability. We inspected installed piezometers, most of which were vandalized, and we took samples for laboratory testing. And the laboratory tests include particle size analysis. We looked at the index properties, mostly the Atterberg limits, and we carried out some consolidated on-drain triaxial tests. And we selected two cross-sections, two critical cross-sections for analysis, for the slope stability analysis, using the Morgenstern and Price method in the rock science software slide. We did a deterministic analysis based on the average shear strength parameters and the observed groundwater levels. Then furthermore, we conducted a probabilistic analysis where the shear strength parameters, the effective shear strength parameters, C' and phi' were considered as the random variables defined by their mean and standard deviation and assuming a normal distribution. So based on the field evidence, all the laboratory reports, we developed a conceptual model of the two cross-sections. This is the first one, cross-section AA, along cross-section AA, and this is the second conceptual model based on the borehole data, inspection pits, laboratory data. So a bit on the slope stability analysis. Usually the measurement of the safety of the slope is the factor of safety, which is the ratio of the shear strength to the shear stress. And the factor of safety is a function of the shear strength parameters, C and phi, the unit weight, the pore water pressure, the slope height, and the slope inclination. Invariably, most of these parameters are known with certainty, except the shear strength parameters, which are C and phi. So in a deterministic approach, it leads, when you do the analysis, you do it once, and it leads to an expectation that the failure of the slope cannot occur under when the conditions where the factor of safety is greater than 1. Because if f of s equals to 1, the slope is at the point of failure. That is, the shear strength and the shear stress are at equilibrium. But when it is greater than 1, the slope is stable. So it doesn't take into account the uncertainty in material properties. Whereas in a probabilistic approach, it accounts for uncertainty and also addresses the variability in material properties, in this case, the shear strength. So the outcome from a probabilistic analysis, we get, when we run the analysis, we get the mean factor of safety, we get the standard deviation, from which we can get the coefficient of variation, which is the ratio of the standard deviation to the mean, and it measures the uncertainty of the output parameter. The higher the coefficient of variation, the greater the level of dispersion and the higher the uncertainty. And also we have the reliability index, which gives us an insight into the reliability of the analysis. Then we have the probability of failure of the slope. So in terms of the input parameters of the shear strength, these are the parameters we used, and we define it by their mean and the standard deviation. Then we have truncation at realistic minimum and maximum parameters. And then we run the analysis for 1,000 or 10,000 iterations between those minimum and maximum values. The computer selects values and gives us the output parameters. So in terms of the result, this gives us a brief description, engineering description of the materials, of the main materials on site, that is the colluvium, the talus, and the shale of the Pietermaritzburg Formation. And the figure on the right just gives us a glimpse of what one of the borehole records. So the particle size analysis shows us that the colluvium is polygraded, a sandy clay. The residual material is polygraded silty clay with minor sand, and the talus is silty clay with minimal sand and gravel, and so the particle sizes range between polygraded and gap-graded soils. And this gives us a summary of the index parameters of the main materials on site. In terms of the consolidated on drain triaxial test, this gives us two examples of the deviatoric stress versus the axial strain for the talus samples, as well as the pore pressures for two samples. And table 3 gives us a summary of the effective shear strength parameters from the consolidated triaxial test. So this is the result of the slope stability analysis, where we ran the deterministic analysis for both slopes. So in the first instance, we have a factor of safety of 1.3, which from a deterministic perspective, it would tell us the slope is stable. And in the case of slope BB, cross-section along BB, it gave us a factor of safety of 1.68. And we looked at the conditions, the groundwater conditions, based on the average parameters under which the slope would fail, because we are not certain at what point the groundwater level would be when the slope failed. So we vary the groundwater level based on the average parameters until we get a factor of safety of 1. That is the point where the slope would fail. And in the case of slope AA, it is within the shale material, and in the case of slope BB, it is at the interface between the colluvium and the talus material. From the probabilistic analysis for both slopes AA and BB, based on the average shear strength parameters, we get the mean values, which are identical to the same from the deterministic analysis, but moreover, we have the standard deviation, we have the coefficient of variation, and the reliability index, coupled with the probability of failure. So both, based on a deterministic point of view, both slopes show an acceptable value of the mean from a deterministic perspective. The values of the probability of failure and the reliability index for both slopes could not, however, be considered to be acceptable, because according to the US Army Corps of Engineers, the expected performance of slopes with a reliability index less than 3 is below average and could be considered hazardous. So whilst the mean values show us that both slopes are stable, but then the values obtained from the reliability indices for both slopes showed us that the performance of those slopes is poor. And we also ran a probabilistic analysis based on the groundwater level at which the slope would fail, and we varied the standard deviation just to see how the slope would perform. So in conclusion, based on the average parameters, both slopes and the prevailing groundwater conditions, they gave us factors of safety of 1.3 and 1.68 respectively, which are indicative of stability. And the probabilistic analysis, based on the average shear strength parameters and the prevailing groundwater conditions for both slopes, gave values of 1.3 for the mean, 28.83% for the probability of failure, and 0.59 for the reliability index. And for section B, we have 1.69, 15.57 for the probability of failure, 1.03 for the reliability index, and the reliability index. So whilst the values of the mean obtained for both slopes indicate stability, the values obtained for beta, which is the reliability index for both sections, suggests the performance of both slopes is hazardous. So, probabilistic approach in slope stability is justified as a result of the variability of the material properties because it takes into account the variability of the material properties. We cannot just take one value and say that suits the entire slope. But however, a probabilistic approach in slope stability should be seen to complement a deterministic analysis and not to replace it. So the probabilistic analysis and the deterministic analysis should go hand in hand. Thank you.
Finally, we come to the end of this session. Before we go for lunch, I would like to say thank you to our delegates sitting here to the end. And I know it's quite difficult to stay here for long hours. Thank you so much. I would also like to thank our presenters. Without your presentation, this conference will be impossible. So thank you so much. I also want to thank our technician. Thank you for your technical support on our conference. Thank you. Now let's go for lunch. See you. And also this afternoon, we have a plenary session, which will start at 1:30. Thank you.